Okay, so a little bit of context on how to read and interpret that slide rule that is going to be provided for you. And I just quickly threw that together, and that's what we're talking about here. This is what's called the slide rule. Okay, and what that means is it allows you to illustrate the order of occupancy for electrons as they fill certain energy levels. So for instance, let's just maybe do an element like sulfur, element number 16. So we know that it's got 16 protons and it's got 16 electrons. If it's a negative element, which it is, and the atomic mass is 32, so it's got 16 neutrons then as well. So what that means is as we're starting in the nucleus, we know there's 16 protons because again, that is the atomic number for sulfur. So what we do is that for every S block, okay, we see can hold 2 electrons. Every P block then can hold 6 electrons. A D block element can hold 10, or P block 10, and the F block on the very bottom of your table holds 14. And what that means is as we look at the S block, notice there are 2 columns. There's where 1 and 2 are from, or what we're referring to as the S block. The P block then has 6 columns, so that's why we say 6 columns for the P block. The D block is right here, which holds 10 electrons, and the F block down here on the bottom. So that's where these numbers are coming from, 2, 6, 10, and 14. So what we're doing is as we follow this slide rule, it says the first energy level, here's our first energy level, 2 electrons, 1s2. Then we go to the top of the next slide, which is a big number 2, means we need a new energy level, and it also holds 2 electrons, 1s2, 2s2. Go to the top of the next slide, it's a 2 here, but we're still in the same energy level, and it can hold 6, and we'll put all 6 in there. So these numbers have to equal 16. So as you can see, we're up to 10 so far, but as we continue down our slide, we see a big number 3, new energy level, that can hold 2, and then we go to the top of the next slide, still the same energy level, the 3, but the P block, and we will only be putting 4 of them in. Because what we see here is 10 and 6 gives us that 16. And how we utilize that is, notice we ended in the 3rd energy level. So we utilize these periods right here. Here's the 3rd period or 3rd energy level. And when we find sulfur, we see it's in the 4th column of the P block. And that's where that 4 comes from. Okay? So that's how you can utilize this slide rule with this table. Okay, so that's an example of what we did for Bohr models, and we did cover those in physical science. Some were perhaps a little more difficult than others. Okay, and for a configuration, if we were to create that, I shouldn't have erased that. I should have left it 1s2, 2s2, 2p6, 3s2, 3p4. Okay, so an electron configuration means we're just depicting a linear representation of these electrons. Okay, and what that means is we've got 1s2, there they are, comma, 2s2, there's those two, 2p6, there they are, 3s2, there's those two, and then 3p4. And notice you add up these exponents, we would get 16. And that's what we're looking for. Okay? And then finally, that of an orbital diagram where you see N, L, M, and S, what that is referring to is N is the energy level, L is a given variable, M, okay, is figured out from L, and then S is the spin. These are your quantum numbers, okay? And what we mean by that, that's what these values are here. These are for your quantum numbers. Basically, it's for the variable L. If it falls in the S block, L is 0. If it falls in the P block, L is 1. If it falls in the D block, L is 2. If it falls in the F block, L is 3. And what that means is, in this depiction, an orbital diagram, we use these arrows, 1s, 1 and 2. There they are, 2s, up, down, 2p. Remember, that can hold 6. Each one of these horizontal lines can only hold 2 electrons. So therefore, we put 2p here. And this is what we like to say we follow the slide rule, okay? And that means, or excuse me, the bus seat rule, that these are empty bus seats, and these arrows pointing up and down are occupants that fill up the bus seats, okay? So each seat is going to fill up with an electron first, then we go back and start pairing them up. We knew we were going to put 6 in there, and there they are. Those are those 6. On to the 3s, 2 electrons, and then ultimately the 3p. Again, each one of these horizontal lines can hold 2, but notice we're only going to put 4 in. And here again, this is how we apply that bus seat rule. Each one of these seats has to have an electron in it, then we pair them up. And these quantum numbers are based off of this electron right here. N is the energy level that the last electron fell into, and that is 3. So N is 3. Okay. Then L is that given value to where you see right here. These are the values for L. So since it fell in the P block, we know that L is going to be 1. And M equals a positive L to a negative L for values. So what that means is, since L is 1, I got these backwards, a negative L to a positive L. Okay? So what that means is, since L was 1, we say negative 1. We don't skip over 0 and put plus 1, because the value for L again was 1. So we put that in for there. There's negative 1. We don't skip over 0, and then positive 1 for that variable. Again, we put 1 in for L, and that's where we get those values. Again, we circled this electron, so therefore M is a negative 1, and then we say that thumbs up means S is a positive 1/2, but if it's pointing down, it's thumbs down, we say negative 1/2. And that's how we obtain those quantum numbers. Okay? So I went through that really quick. Hopefully this is a quick tool that you can use to help you fill out the Bohr model, which is electrons rotating around the nucleus, an electron configuration, which is a linear depiction of the Bohr model. Then finally, an orbital diagram is where we use these to figure out our 4 quantum numbers. Okay? And you can take a shortcut for these. It's called a noble gas configuration, but we'll explain that again at a later time. If you have any questions, just ask.